Hi, grade 10s. Before we start, I would like to answer the question, what is 1 mole of particles? And I found this great TEDx video about the mole, and I'm going to share it with you now.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Hi, grade 10s. Welcome to the second session for the winter school. Today we're going to be looking at a very important link that helps us in quantifying chemicals. And yesterday you saw that the mass of the reactants before a reaction must equal to the mass of the reactants after a reaction, because no matter is created or destroyed. So in a chemical reaction, all the atoms of the reactants rearrange to form new compounds. And we're going to look today at how the relationship between one particle, in other words, one atom if it's an element, or two if it's a molecule such as oxygen, and the mass of one formula unit or particle in a molecule relates to what happens if we have a whole bunch of those particles. And we're going to look what happens when you have the mass of one atom. You compare the mass of one atom to the mass of Avogadro's number of particles. And you'll see that there's quite a distinct relationship between this, and this is what allows chemists to be able to use the periodic table and accurately determine the mass of substances that they need to react together to get a certain amount of product. So we're starting off here at the periodic table. So just to remind you, and this key is very important, there we have the copper, the key for copper. So Cu is the symbol, and we all know that Cu stands for copper. There's that number 29, the atomic number. Then there is also the relative atomic mass. We'll ignore the electronegativity for now. But what does that atomic number tell us? Can you remember from what you learned in grade 8? What does that relative atomic mass number mean? So today we're going to look at what those numbers mean and how those numbers are very important in helping us understand the mass relationship between one particle and Avogadro's number of particles. So I just want to go back to atomic structure so that you can understand this quite clearly. Remember, atoms consist of a nucleus, and in that nucleus you have protons and you have neutrons. Surrounding the nucleus are the shells of electrons. So the number of subatomic particles in an atom can be calculated from the atom's atomic mass and its atomic number. So let's see how we can do that. So firstly, the atomic number and mass number. Remember, the atomic number is the number of protons in an atom of an element, and that is its atomic number. So hydrogen, which has an atomic number of 1, will have 1 proton. Helium has an atomic number of 2. It will have 2 protons. So all the atoms of any given element will have the same number of protons. And atoms of different elements will have a different number of protons. So hydrogen has 1 proton. Helium has 2 protons. Lithium has 3 protons. And an atom, a neutral atom, contains an equal number of protons and electrons. And since protons and electrons have equal and opposite charges, that is why the net charge on an atom is neutral. It has a neutral electric charge. Now we can look at the mass number. Okay, the mass number is the number of an atom. It's the total number of protons and neutrons. So atoms of different elements usually have different mass numbers, although they can be the same. For example, the mass of argon atoms and calcium atoms can both be 40, based on the number of neutrons that are in the atom. But now let's look at sodium, for example. Okay, just going back to the example here. Sodium is element number 11. Every sodium atom has 11 protons and 11 neutrons. It has 11 positive charges and 11 negative charges. But now coming to the mass number. Okay, Okay, remember there's the mass number, 23. That is the atomic number, 11. So that's an easy way to write the symbol to show both the mass number and the atomic number. So how do we calculate the number of subatomic particles? Well, the 11 tells us sodium has 11 protons. The 23 is the mass number. The mass number is the sum of protons plus neutrons. So the total number of neutrons would be 23 minus 11, which is 12. So this sodium atom will have 12 neutrons. And so there's the question. The atomic number of sodium is 11 and its mass number is 23. Calculate the number of protons, neutrons, and electrons. So we reveal the answer. Number of protons equals 11, number of electrons equals 11, and the number of neutrons is 23 minus 11, which is 12. So now we are going to use that mass number to work out or determine the mass of one atom of different elements, and then later we'll come back and we'll look how we can do the same for a compound, how we can use that mass number to find the relative formula mass of a compound. So I have a couple of Bohr diagrams here of different elements. So there I have carbon, magnesium, sulfur, copper, calcium, zinc, iron, and lead. So instead of asking you to count the actual number of protons and neutrons, that symbol there, P6, is protons 6, N is the neutrons 6. So carbon has 6 protons and 6 neutrons. Let's now use that to look at the molar mass of different substances. Okay, so there we have the mass of one atom of carbon. So it's the mass of one carbon atom is 6 protons plus 6 neutrons, which is 12. The U means atomic units. The mass of one atom of sulfur, 16 plus 16 is 32 atomic mass units. Iron, there's iron. The mass of one atom of iron, 26 protons plus 13 neutrons is 56 atomic mass units. Now, if I had 1 mole of carbon atoms, now the mole is 6.2 times 10 to the 23. Okay, so just to give you a brief overview of Avogadro's number. Okay, Avogadro's number is a number of units in 1 mole of any substance. So think of Avogadro's number like a dozen. We all know that there are 12 in a dozen. So if I have 1 dozen eggs, we know that I have 12 eggs. If I have 2 dozen eggs, then I have 24 eggs. So Avogadro's number is similar to the dozen. It's almost like a counting unit. Okay, so Avogadro's number is equal to 6.022 times 10 to the 23 number of particles. Those could be units, those could be electrons, atoms, ions, molecules. It could be any particle of substance. So that's a large number. Okay, so now if I had 1 mole of carbon atoms, or 1 mole of sulfur atoms, or 1 mole of iron atoms, okay, then the mass of that 1 mole of carbon would be 12 grams. Of sulfur, it would be 32 grams, and of iron, it would be 56 grams. So, if you can see here, the relative atomic mass is 12 atomic mass units. If I had 6.022 times 10 to the 23 carbon atoms, they would have a mass of 12 grams. For sulfur, it's 32 atomic mass units, but 1 mole would have a mass of 32 grams. And for iron, it's 56 atomic mass units, but 1 mole would have a mass of 56 grams. So coming back to the periodic table. Okay, that mass number is the number of protons and neutrons for one atom, and if I had 1 mole, then that would be the mass in grams, 63,5. Now, that 63,5 means that copper must have half a neutron. So think about that. Is that possible? If you've got a decimal there, what does that mean? So if you have a mass number that is as a decimal, it means that the mass that is given there to you is the average relative atomic mass of the different isotopes of copper. So here I've got some. It's activity time now. So I want you to go to the worksheet and you're going to see the pictures of the substances that I showed you. I want you to go to the periodic table and find the relative atomic mass of each of those elements. And then when you've done that, what do you think what will the mass be if I had Avogadro's number or 1 mole of each of those elements? And we will leave it there, just looking at elements for now. You can take a break and come back after the break, and we'll look at how to do this for compounds.